Hi, my name is Wen Xu and my project is called Cancer Detection in Gigapixel Pathology Images. The objective of this project is to build an end-to-end detector that can output a heat map showing regions of slide likely to contain cancer. The data I use are from Chameleon 16 Challenge, since our professor has kindly made some tumor masks for us. In this project, I only used the data from Google Drive. Firstly, we need to get image patches and their labels. This is the piece of code that I used in this part. Since the original slide images are all in gigapixel size, which are not efficient to read. Besides, we only have a small number of slides available. Therefore, I divide one slide image into smaller patches to get more training data. The window size I used is 299 by 299, and the stride between the slide window is also 299. The label of each patch is decided by the corresponding tumor mask. If over 1% of the pixels in the window are tumor cells, then the image patch will be labeled as tumor. Here we can see how the slide window moves row by row. With the approach mentioned above, I used Tumor 91 to prepare data for model training. We slide the window across the image and the mask at the same time to get patches and their labels. For example, the green patch will be labeled 0 and the red patch will be labeled 1. In order to improve the efficiency, we will ignore the patch if the percentage of tissue pixels in that patch is less than 20%. For example, the blue patch in the image will be ignored. In order to increase the number and diversity of data, I use data augmentation, including rotation and flipping in this project. In this way, we can get 5,544 patches labeled tumor and over 288,000 patches labeled healthy, which is very imbalanced. Therefore, we randomly select 5,544 patches from healthy examples and get a dataset of about 11,000 patches. Then we divide them into training, validation, and testing data by 60%, 20%, and 20%. Here are two patch examples that we get. One is a healthy patch labeled 0 and the other is a tumor patch labeled 1. We use transfer learning to build the model in this project. The base model is a pre-trained network Inception v3 with tops removed. I added a dense layer, a dropout layer, and an output layer on top of the base model. The optimizer I used is RMS probe, and the loss is binary cross entropy. After feeding training data into the model, we can extract features with the base model and train the custom layers with these features. I ran the training process for 30 epochs, and the model is saved after each epoch. From the plots of accuracy and loss, we can tell that the model is overfitting after the 5th epoch. Therefore, I load weights in the 5th epoch model each time when I do testing and predictions. The model could reach an accuracy of 91% on the test data. I used Tumor 110 to make predictions. I first define a prediction image with shape of 299 times downsampling the level 0 slide image, with all pixel values initialized as 0. Then I use slide window to get the patches in level 0 image, ignoring those with less than 20% tissue pixels. By predicting the label for each patch with the model, we can get the corresponding pixel value in the prediction image. For example, the IJ's entry corresponds to the red patch and will be 1, while the PQ's entry corresponds to the green patch and will be labeled 0. Here we can see the prediction achieved by our model. From human judgment, it's very close to the ground truth. The evaluation metrics I use here are F1 score and accuracy. By comparing the ground truth mask and the predicted results, we can calculate the true positive, true negative, false positive, and false negative pixels. In this way, we can get the F1 score and accuracy for the results, which are 85.4% and 95.5% respectively. It proves that we have achieved pretty good results. Possible further extensions include getting training data from more slides. I tried this, but the collab always died when the data size was huge. I'm also going to try fine-tuning to see whether accuracy can be enhanced and to predict on several other slides to better evaluate the performance of the model. I also plan to try multi-scale model mentioned in class. That's all for my presentation. Thank you.